This video is over lesson 41, functions, and it's for my pre-algebra classes. So, ladies and gentlemen, a function is a mathematical rule that tells how one number, the input, is turned into another number, the output. And you can kind of almost imagine this like a mathematical machine, a function machine. And so here I've got my machine and it's switched to the on position, so things are going to go in the machine. So like, I don't know, 6, -4, 3, and then out the other side, something's going to come out. So this machine's gonna chomp them up and do things to them, and something's going to come out on the other side, like maybe 13, -7, and +7, let's say. And so there's something that's happening to each of these. Now, if you pause the video and take a moment and maybe consider, I actually did choose a function, something to happen to each of these inputs that leads to each of these outputs. So just see maybe if you can pause for a second and see if you can figure it out. So in this case, I went ahead and I decided that I was going to double the number and then add 1 to it. So 2 times 6 is 12, plus 1 is 13. 2 times a -4 is a -8, but then plus 1 would be a -7. 2 times 3 is 6, but then plus 1 is a +7. So that would be an example of a function there. Now, real quick here though, let's put a star after this definition here. There is one more important part to a function that we need to keep in mind. So in order to be a function, it's not just about inputs and outputs, but there's one more condition that must be met. For every input, there is only one output. And if we put it in terms of the machine here, if this is a machine in a factory and I'm producing certain things and I box them up and I ship them out to my customers, I need to know that when I put a 6 in here, a 13 is going to come out every time. I need to know when I put a -4 in, a -7 is going to come out. I need to know that when I put in a 3, a 7 is going to come out. On the other hand, if I put in a 3 and one time I get a 7, but then I put a 3 another time and I get out an 8, then I can't depend on that. That's a problem. Something's broken in my machine. That's not a function. So for every input, there's only one output. So we're going to take a look at a few examples here. And in particular, we're going to take a look at these examples in what's called a table of values. So when you make a table of values, the input always goes on the left and the output on the right. And so you'll see I have that in red. So on the homework, you're not actually going to write input and output, but you'll put whatever those inputs and outputs are. Often it's going to be X and Y, but sometimes it can be other things. Like if we're finding the area of a square, the input might be the side length, but then the output would be the area. So input, output, X, Y in this case. So if we look at this, would this be a function? And if we look closely, we see -6. If we put in -6, we get out 6. If we put in 3, we get out -4. We put in 5, we get out -3. We put in 8, we get out 9. We put in 5, we get out 7. So the big thing to watch for is, for every input, is there only one output? So every time we see -6 being put in, do we see 0 coming out? Yes, that's good. For every time we see 3 being put in, do we see -4 coming out? Yes, we do. There's only one place we see it, so yes. Every time we see 5 being put in, do we see -3 coming out? Oh, no, we don't. Because down here I'm putting in 5, but I'm getting out 7. But up here I put in 5 and I get out -3. So this is not a function. So the answer, is this a function? No. Because when x equals 5, or in other words, for the input 5, so because when x equals 5, y can equal -3 or 7. And that's not allowed. So if we come over here to this next example, okay, so take a moment, look that over, see if you can figure out if that's a function. All right, so let's look at it again. So the key here is for every input, there's only one output. So every time we see a -6 being put in, do we see a 0 come out? Yes. Every time we see a 3 go in, do we see a -4 go out? Yes. Every time I see a 5 go in, do I see a 7 come out? This time, yes. Every time I see an 8 go in, do I see a 7 come out? Yes. And every time I see a 9 go in, do I see a -3 come out? Yes. So this actually is a function. Now, what often trips students up at this point is the fact that there are two things that both have an output of 7. And that's not a big deal, because what matters here is this stuff leading to that stuff. That every time we have the same number here, it needs to come out with the same number here. So this actually if the y values had been the same, it would have been a function. So if this was 5, 7, and 5, 7, this actually would have been a function, because every time we saw a 5, a 7 came out. Or if these were both -3, every time a 5 went in, a -3 came out. That would have been a function. Okay, so that's the condition. It needs to be every time we see one of these guys, it leads to the same thing over here. Now, this isn't a problem because every time I see a 5, I get a 7. Every time I see an 8, I get a 7. That's fine. Now, it just so happens that two things lead to the same output. That's no big deal, though. Okay. So, being the same output doesn't matter. So is this a function here? Yes. We're going to make a note here. It's okay. It's okay that x equals 5 and x equals 8 both result in y equals 7. That's fine. So again, if we compare this to our machine in our factory, all this would mean that is if I need to get a 7 out to a customer, that means I can put the ingredients for 5 in or the ingredients for 8 in, and it'll come out with a 7. So there's just two different ways to get that product. And that's fine. That's no big deal. Now over here, this is a problem because if I put in a 5, am I going to get out a -3 or am I going to get out a 7? Well, if I put in the ingredients of a 5, the input of a 5, and my customer has ordered a 7, but out comes a -3, well, that's no good. I can't ship the customer a -3 when they ordered a 7. Okay, so if we think about it in that terms, we need to depend on the input always leading to the same output. But there can be more than one input that leads to the same output. And that's the big twist here that we got to get used to. At this point, we're going to switch gears here and we're going to take a look at how to discover from a table of values the equation for that. And so a lot of these you might be able to just quickly find for yourselves. So for example, this one, we have input of 3, we output 9. When I put in 4, I get out 10. When I put in 5, I get out 11. When I put in 6, I get out 12. And I imagine this one's pretty easy. You may be able to figure out what the rule is here. So because we're getting out the y value, the output, then our equation should start with y equals. And so basically this is giving me instructions. If I want to find out what y equals, what am I going to do to that input? And this one should be pretty easy because you should see that each time we're taking our x value and adding 6. And so that literally becomes my equation. If you want to find the y value, it's equal to the x value plus 6. That's what that equation means. Now I'm going to draw your attention to something that can potentially be helpful later on, and that's a little thing looking for patterns here. So if you notice that each time here, the x values kept going up by 1. And my y values also kept going up by 1. So we keep changing by 1. You can actually find important information by looking at this pattern. So these changes right here are what we can call delta y. So delta is just a Greek letter. It looks like a triangle. It's a Greek letter that means change. So how are your y values changing? They're changing by going up 1. Over here, the change in your x values then would be delta x, and they're also going up by 1. So if you take your delta y over your delta x, so delta y over delta x, so 1 over 1, and simplify that, that is actually going to be the number often that's going to be multiplied in front of your variable. So this time we don't have anything multiplied in front of the variable because it's really just that invisible 1. So sometimes if you're feeling a little stumped, that's a good little trick to use. All right, well now that we have our equation, let's go ahead and fill in our empty space. So if we want to find this y value, it's going to equal the x value, 10, plus 6, which is 16. All right, let's look at our next one. We're going to move down here to the corner. So take a moment and see if you can kind of find a pattern there. So you may have already spotted the pattern. In order to find the y values, so we're going to start with y, it's going to equal what are we doing to the x values? Well, if we put in -6 and we get out a -2 and get out a -6, put in a -1, get out a -3, put in a 0, get out a 0, put in 1, get out 3, hopefully you're noticing we're taking the x value and multiplying it by 3 each time. So 3 times x, or just 3x. And that's, again, another really simple one. And sometimes they're going to just be that obvious, and you can just write them down, and you're all set to go. I do want to look at that delta thing again. So again, my x values keep going up by 1. So my delta x here was 1, but my y values, notice that to go from a -6 to a -3, that's going up 3, and then to go to 0, that's up 3 more, and then up 3 more again. So my delta y this time was 3. So if we do that delta y over delta x thing, we get 3 over 1, which is just 3. And notice that's the number that we're multiplying with x. So if you were feeling stumped about this, weren't quite sure what to do with this, looking at those deltas, looking at those changes can be a help for finding your equation much of the time. All right, we're going to move over to the next one now. So put in 5, get out 25, put in 6, get out 36, put in 7, get out 49, put in 8, get out 64. And if you look at this one, there's a chance that the equation just might kind of stand out to you. Because what we're doing each time really is just multiplying the number with itself. 5 times 5 is 25, 6 times 6 is 36, 7 times 7 is 49, 8 times 8 is 64. And so we're multiplying the number with itself. So we're taking x and multiplying it with x. Now, when you write that though, x times x simplifies to x squared. Oh, and I realize, let's go back here, we forgot to fill that in. So to find this missing y value, it's going to equal 3 times the x value. So 3 times 2 is 6. All right, so back over here then. If I look at my delta x's, so this is going up 1, up 1, up 1. So my delta x again is 1. My delta y's, though, 25 to 36 is going up 11. 36 to 49 is going up 13. And 49 to 64 is going up 15. And so here we do not have a constant delta y. And so since delta y, it is changing, but it's just not a single number. So it keeps changing. And so because of that, that means that our equation's not going to be just as simple as this right here or that right there. And we see that because there's a square in it. So that square is more complicated than just multiplying or adding. All right, so if we finish this off then, to find this last y value, it's going to equal the x value squared. So 9 squared, 9 times 9, is 81. And this last one, go ahead and pause the video and see if you can find the equation for this one. Now this one, I have found over the years, tends to stump students a fair bit. And so this is where especially I would encourage you to go back and check out that delta x and delta y that we've been kind of talking about. So it's going up 1, going up 1, going up 1. Over here, this is going up 2, going up 2, and going up 2. So my delta x is 1. My delta y is 2. And so since that's nice and steady, I can go ahead and do delta y over delta x. So delta y is 2, delta x is 1, so this is going to come out with a 2. So therefore, when I'm writing my equation, I'm going to have a y equals 2 times x, because that 2 is going to be what I multiply with x. Now, if we look at this, though, that's not going to be good enough, because if you do 2 times negative 2, we should get negative 4. But instead, we get negative 7. If we do 2 times negative 1, we should get a negative 2, but instead I get a negative 5. If I get 2 times 0, I should get 0, but instead I get a negative 3. So if you look, though, each time what's happening? So what happens to a negative 4 that pushes it back to a negative 7? A negative 2 that pushes it back to a negative 5. A 0 that pushes it back to negative 3. Or in this case, 2 times 1 should be 2, but then we're pushing it back to a negative 1. Well, each time you're going back 3. So we're taking our 2x, but then we have to modify it by subtracting 3. So if your delta x's and your delta y's are all the same, you can use this trick to find the number that's going to go out in front of x, but you may still have to adjust your equation by adding or subtracting. And so now that we have the equation, let's go ahead and finish this off then. So to find the y value, we're going to do 2 times the x value. So 2 times 2 is 4, and then subtract 3, 1. And now we're going to go to the back. So on the back, we're going to do some slightly different things. First of all, I want to do some graphing. So when we want to graph a function, what we need is points. We need enough points that we can find the shape of the graph and then connect them. So typically what we want to do is we'd like a few points on either side of the y-axis. So since x is my input, I'm thinking left and right values. So typically I like to go, let's see, let's start on the left with like a negative 2 and work our way up to a positive 2. That's usually a good spread right there. Gives us a nice amount of points that we can kind of find the shape of this. So if we follow the equation to find the y value, it's going to equal 3 times the x value. So 3 times this x value, 3 times negative 2, well 3 times 2 is 6, but then we still have that negative. Then 3 times the negative 1, 3 times 1 is 3, but we still have the negative. 3 times 0 is 0, 3 times 1 is 3, 3 times 2 is 6. And so in order to graph it, we're literally going to take our x and our y value, and these become a point. So that just becomes the point -2, -6. This then becomes the point -1, -3. This becomes 0, 0, the origin. So this graph is actually going to go through the origin. This would then be 1, 3, and this would be 2, 6. So just the points just come together. So let's graph each of these. So 2, -6, -2, -6. So the first number tells me left and right, so left 2, and the second number tells me up or down, so down 6. 1, 2, 4, 5, 6. There's my first point. Next point, -1, so left 1, and then -3, down 3. 0, 0 is the origin. That's nice and easy. Make sure that's big enough that we can see it. And then 1, 3, so 1 would be 1 to the right, and then 3 would be 3 up. And then finally 2, so 1, 2 to the right, and 6 would be 6 up. And there's my 5 points. And we can see that these all fall on the same line. So I'm going to do the best that I can to draw a line through those. And so since these make a line, this actually is what's called a linear function. So linear function because it makes a line. And that is a vocab term there. So linear is just the adjective for line. Now, one more thing that we're going to take a look at here is a thing called proportional functions. So we've learned about proportions. Proportion is a statement that two ratios are equal. So what we're going to do is we're going to take kind of that delta y over delta x that we did on the front, and we're going to take the deltas off. So no more deltas here. It's just going to be y over x. That's going to be our ratio. So in this case here, this would be a -6 to a -2. This would be a -3 to a -1, -3 to -1. So y value on top, x value on bottom. This would be 0 over 0. This would be 3 over 1, and this would be 6 over 2. So if this is proportional, then each one of these y over x values, each one of these ratios, should equal the same thing. So if we simplify this, 6 divided by 2 is 3, but a negative and a negative will cancel. So it's just 3. 3 divided by 1 is 3, but then two negatives cancel and make a positive. 0 over 0 is undefined, and we're not going to let that worry us. We're basically just going to, that's going to be a freebie. We're going to skip that. As long as everything else is equal, we're good. So you get a free pass for the undefined one. Down here now, 3 over 1. 3 divided by 1 is 3, and 6 divided by 2 is 3. So we can see that each one of these ratios is equal, and so that is the definition of a proportion. So yes, all ratios are equal, which means that this function right here, this graph, is a proportional function. Let's take a look at the next example now. So new equation, y equals x plus 3. So last time it was 3 times x, this time it's x plus 3. I like the same spread of numbers we had before, -2, -1, 0, 1, 2. That's a good group to go with. Unless you have a really good reason for choosing other values, that's a good group of numbers to choose. So we'll see in a second here when you might want to change your mind on that. So I will tell you this, if there were like a 1/2 x, then I wouldn't want to do odd numbers because they're not going to multiply nicely with 1/2. I'd rather choose even numbers. So in that case, I'd rather do like -4, -2, 0, 2, 4. and choose all even numbers. Or if it was a 1/3, I want to do all numbers that are multiples of 3. So that way the 1/3 times that multiple 3 will simplify nicely. But since this is just x plus 3, adding 3 to something, not a big deal. So we do want to choose a few numbers, though, that are going to be on the left and a little on the right. So now let's go ahead and plug in our values and find our outputs. So to find the y values, it's going to equal the x value plus 3. So this x value, -2 plus 3. So they're opposite signs, different signs. So we're going to subtract them. So 3 minus 2 is 1. But then the positive 3 is bigger. So it'll be a positive 1. Then -1 plus 3. -1 plus 3, again, they've got different signs. So we're going to subtract. 3 minus 1 is 2. But the 3 is bigger than the 1, so it's still going to be positive. And then from there it gets real easy. 0 plus 3 is 3. 1 plus 3 is 4. And 2 plus 3 is 5. So if we graph this one out, I'm not going to write all the coordinates over there. Hopefully you got the idea from the last one. So the first point is -2, 1. So that's going to be 2 to the left and 1 up. The next one is -1, 2. So that's 1 to the left, but then 2 up. Then we have 0, 3. So 0 means not moving left or right at all. So we're just moving up 3. 1, 4. So the 1 is 1 to the right, and then 4 is up 4, because it's positive. And then 2, 5 would be 2 to the right and 5 up. And if we look at these are all nicely in a line. So sure enough, this one again is linear. This is a linear function. Now, if we take a look at, is this proportional? We're looking at the ratio of y over x. Y over x. And so that's going to be a 1 over a -2. Here it'll be 2 over a -1. This will be a 3 over 0, 4 over 1, and 5 over 2. And if we simplify each of these now, 1 over 2 really is 1/2. But then a positive divided by a negative would make that a -1/2. And then 2 over a -1, well, 2 divided by 1 is a whole number 2, but then that negative is going to make that a -2. 3 over 0 would be undefined, so that's our freebie, don't worry about that. 4 over 1 is 4, and then 5 divided by 2 is 2.5 or 2.5. And so we look at this, in order to be proportional, all the ratios have to be equal. So is this proportional? No. So technically we could have stopped right here. The moment we saw that two of the ratios were not the same, we really could have stopped. I wanted to complete the chart just to have the chart done. But on the homework, once you have two that don't match, you know right away that this is not proportional. It is linear, but it's not proportional. Which brings us down to the last one here. So now to graph this, a equals s squared. This looks like the area of a square. So if we're looking at the area of a square, and I want to graph this out, you really don't want negative side lengths, so it doesn't make sense to start with a negative. In a lot of ways, it would make sense to start with positive numbers. However, I am going to make one exception. I am going to start with 0. Not because we would actually have a square with a side length 0, but this gives me kind of a starting place because the length of my sides can start right after 0. And so I want to be able to connect that. So I'm going to put 0 in just to kind of be kind of a starting place. So now if we put our inputs in, so A, the output, will equal the input squared, s squared. So 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. And 4 squared is 16. So graph our points here. You can see I've already got my coordinate plane set up. It's just the first quadrant. So my first point is 0, 0. That's going to be right here. So right there where the two axes meet. 1, 1, so 1 to the right and 1 up will be right there. Try to get that out of my glare there as much as I can. And then 2, 4. So 2, 4. Ooh, that glare is bad. Is that better in the shadow? It looks like it's better in the shadow, actually. All right, so 2, 4 would be 2 to the right and 4 up, right there. 3, 9 would be 3 to the right and then 9 up, so right there. And then finally, 4, 16 would be way up here. And so if you look at these do not form a line. So the graph of this is actually going to be a curve. We'll learn more about that curve later, but that's actually a special curve called a parabola. To be fully honest about this curve, it's actually only half the curve. There's another half that'd be on the other side of the y-axis. So if we look at this, this is not linear. This does not make a line. So when you have a square in your equation, it's not going to be a line. So here, to find out if this is proportional, it's going to be the output over the input. So output over input will be 0 over 0, 1 over 1, 4 over 2, 9 over 3, and 16 over 4. So if we simplify each of those, 0 over 0 is undefined. That's your freebie. Don't worry about it. It is undefined, but just move on. So here, 1 over 1 is 1. Here, 4 over 2 is 2. And technically on the homework, you could just stop there and say, we already know right now that it is not proportional. But just to complete the chart, 9 over 3 is 3 and 16 over 4 is 4. So are these proportional? No. This is not a proportional function. So there's something special about this first one. It was proportional, and there's two things that it has that the other two are both lacking. And so those two things are proportional functions as a shortcut. If you look at their graphs, there are two things you're looking for. One, you're looking to see that they're linear. So that's where this last example fails, is it's not linear. Now, this one is linear, but it's not proportional. So what does the first example have that the second one's missing? Well, that's point number 2. So proportional functions are linear, and they go through the origin, 0, 0. So this was linear, but it didn't go through the origin. So as long as your graph is linear and it goes through the origin, it'll be a proportional function. And go ahead and grab a highlighter real quick, and we just want to put a little box of emphasis around that right there. So if you want to know if it's a proportional function just by a quick glance at its graph, is it linear? Does it go through the origin? Now on the other hand, if you're given a table of values, you can find out if it's proportional just by comparing each of the ratios. And that, ladies and gentlemen, is the end of our lesson.